try to evaluate this infinity y minus y to y y dx dy dx x is y square. And the suggestion is try u to x square minus y square v y square. Found the Jacobian, sketch the area, and determine the limits. And then use the integrating in u and v, evaluate the inequality. Okay, let's try. So transformation is like that. Jacobian. Jacobian is the determinant, the absolute value of determinant. Define it as absolute value. So u plus x, u plus y, b plus v plus y, right? It's the determinant, and then take the absolute value, and we'll figure out the sign by the limit, because obviously this integral is positive, right? X is absolute value. Y is from 0 to infinity, so y is positive, right? And exponential function is positive, so the whole thing is positive. Okay. But we got this first. Partial u partial x is 2x. Partial u partial y is minus 2y. And 3 partial x is 2x. Partial v partial y is 2y. Which is 4xy plus 4xy, 8xy. xy as and this part absolute value. Right, that's J. Is okay. So the change of value, change of integration. First, figure out the area integral. Question? Yeah. No? 8 is a number, right? Doesn't matter. 8, and this absolute value x and y. Just I'm taking absolute value because when we transform the area, we usually assume it's positive. But and then we use the limit of how you integrate to make sure that it's positive. That will simplify a little thinking, because determinant itself has a sign, right? And it's a little complicated to figure out what the sign is, right? And so it's sometimes easier. I mean, most of the time easier to figure out to make sure that it's positive by choosing the limit. We'll see how we do it. So let's sketch the area. Originally x and y, and you integrate y from 0 to infinity. So obviously not x, it's the other way around. Y, right? And then x is the integration x is from minus y. So whatever y is from here, there's an integrate from 0 to 0 to infinity, and x is from minus y to y, so you have 45-degree lines in this area. So for x is for a given y, you integrate from here, right? That's so this is the, and then so this is the area bounded by these two diagonal lines, right? And now we try to figure out u and v, and for fixed u and fixed v, for fixed u, you see that this is an equation of a hyperbola. For fixed v, this is an equation for a circle, right? So the hyperbola is when x is 0, this is all negative along x equals, or along the y-axis is all negative because minus y squared, right? So and the hyperbola is something like that. This line, so you have hyperbola, different view, right? And on this axis is minus y squared. So this is constant u, so this is u. All these are u equals to minus u is x squared minus y squared, right? And we got that's okay. So we figure out, and the limit obviously at the origin u is this is u equals to 0. Obviously x and y, both x and y is 0, and so you and then it's all negative. It keep decreasing given u all these hyperbola at infinity. Then obviously u is equal to minus infinity. So u mean is minus infinity. U naught is 0, right? But that's this integration over this area, right? And now for v, for constant v, these are circle. Like you can draw a circle, something like that. Not a very good sketch, but a circle. Right. These are constant. These are constant v. These are v is squared plus y squared. And obviously also at the origin v is 0. At infinity, all these circles move up, then it's all positive. So v is infinity, right? So v mean is 0. V max is infinity. Okay. All right. Then we can now do the transform. Try to evaluate. Well, at these are the curve of constant u, right? So these are like the coordinate line of u, constant u, and at the origin, both x and y is 0. So obviously u is 0, right? And then as you move up the y-axis, which is this original integration area, you move up, right? And on at the x equals 0, then this u is just minus y squared, so in all negative. So as you move up, it become more and more negative. As y goes to infinity, then u obviously go to minus infinity. So at x equals 0, y is infinity, so u is minus infinity. So you have all these hyperbola, then at infinity you have the hyperbola, which is u is minus infinity, right? Is that okay? So the range of integration for u is from minus infinity to 0. Is that okay? And likewise, for u for v along the y-axis, x is 0. It's all positive. As you move up all these circles, the value of v is increasing and goes to infinity. So V max is infinity. Okay. Okay. Now understand. Because this is the original area, right? Original, you integrate from 0 to infinity. So you need to map this area for the range of x and y, and then map it to the new coordinate system, which is defined by u and v. So you need to figure out what the value of u and v to integrate. Is that okay? And that is the integration range. So like now I write it to transform from dx dy to du dv. So now u is minus infinity to 0, and v is from 0 to infinity. Is that okay? And because du and dv are both increasing when you choose the limit this way, then all we need to do is just transform the Jacobian, because originally dx dy, now you change it to du dv, so you need to divide it by the Jacobian, is 1 over j. Right? This j go into here. Right? That will make this du dv divided by j is equal to dx dy. Is that okay? You understand this step, right? So this Jacobian we define as this matrix, right? And we have the derivative of the new variable with respect to the old variable, right? And so you can say that dx dy right, multiplied by j would be equals to du dv. We have this relationship, and therefore dx dy is du dv divided by j. Okay. All right. Then other things. You have y and x, and in this case, you actually don't need to do transformation because you know that j has an x and y, so you just stay there. So x and y, because that will cancel with this j, and then exponential function. This is minus 2x plus x squared plus y squared. X squared plus y squared is just v, right? So it's minus 2v. Is it? Did I get it correct? Did I copy it correct? Is it minus 2? This is 4. Okay, okay. This is 4. Is it really like that? Something like that? All right. One more thing is this. We need to figure out what this is. Shouldn't be too difficult because we first can just solve for x squared and y squared in terms of u and v. So x squared obviously is you add the 2 divided by 2 will give you x squared. So then we have u plus v, right? You add the 2, you get rid of y, add x squared plus x squared, so we divided by 2 will be x squared. The y squared would be the other way around, so it's v minus x, v minus u, get rid of the x, and give you minus 2 y squared, v minus u. Okay, and then so it's 4 plus y 4 is the square of all these, the two terms, sum over the square, so it's 1 4. We have u squared plus v squared plus 2uv plus v squared plus u squared minus 2uv. Right, so those two cancel. All together is 1/2 of u squared plus v squared. Right. So that's not too bad. Minus 3 and then j, that's 8xy. So, and x and y, we already determined that they are all positive in the original integration. They're all positive. So this two cancel. This whole factor is just 1/8. Right? So,
isn't there in the exponent there to begin with, so it just goes b squared plus b squared?
oh yeah, the two. Yeah. Okay. Yeah. All right. So the next step is this is next step is just 1/8 integration. You now is separable, so you can separate minus b from dv. And both factors are Gaussian integral, and you know how to integrate that. That will give you the final answer. Right? Is it okay? This should be all the steps. Right? Yeah. Any more homework questions? Is that okay? Is it the whole thing? Did I answer all the parts? Jacobian, at first we calculate this a times absolute value x and y, right? So that's a times x and y, and multiplied by the original x and y factor, right? And we determined that originally both are positive. This absolute value is positive. Y is positive because you integrate from 0 to infinity, so that's positive. So this is a positive factor, and j is a positive factor. So you divide it by that, so that will leave you just 1/8, right? Yeah. Why is this one? I erased that one. So that is how we do variable transformation, multivariable transformation. You multiply by or divide it by the Jacobian, right? So let's see, let's do some spacing. So dx dy is the Jacobian. Multiply by this Jacobian, if we define the Jacobian this way, so this Jacobian is du dv. Because this Jacobian is the derivative of the new variable with respect to the old variable, right? And then you multiply by the area of the old variable, that will give you area in the area element in the new variable. Right? If we define the Jacobian this way, you can also define another Jacobian. You can define that like J prime is partial x partial u partial x partial. Say that again. I didn't. Yeah, it's because this is the relationship where you can also always divide this j together. Right. Yeah, that's true, and that's the that is true. Yeah, right. That is true. You can work that out. I think your textbook has a discussion there. Probably didn't discuss that, but they are actually you can accept that as a fact for now. So you can define a j prime like that. So originally it's like that, right? J, if you define j like that, but you define j prime like that, then it's j prime is over here, or you can divide j prime over here. And you can work that out if you like. You can do the inverse relation and do this derivative. So this is plus x plus u there's a square root of that, and it's a little bit complicated. That you can say is minus 2x, right? X, or you can say 2x dx du as u as, you can say 2x dx a partial x partial u is 1/2 here, right? So partial u partial x is 1/4 of x, right? And partial x partial v is the same, so it's just 1/4 of x. Partial y partial u is, we have a negative sign. 3, 4, 1. Right, and then partial y partial v is the positive sign on the 4. Altogether, you multiply by 1/4 times or 16, but you have two of them, so 1/8. 1/8. This is just 1/2. Right? You can work that out explicitly and show that that's the correct way. Yeah.